All right, hello everybody. I'm Ricardo, and I'm going to present you our paper reviewing FID and SID metrics on generative adversarial networks. Yeah, I'm Ricardo, and I'm from the Netherlands originally, but I'm now currently studying in the United States, 20 years old. And well, I'm currently doing my master's in data science. And yeah, I'm also an active TA and a researcher in the field of computer vision. And yeah, today I'm going to talk about how the metrics FID and SID function on a variety of GANs. I'll talk in a second about what GANs are, but first our objective. Yeah, so we're going to measure FID and SID metrics, which are two metrics to measure the performance of GANs on two separate image-to-image GANs. Those are Pix2Pix and CycleGAN. And we'll train those GANs on our custom data sets called facades, maps, and cityscapes. Eventually, we had the goal to see if a GAN performs better in a certain domain, so on a specific data set, and also how both metrics behave. But first, let's talk about GANs. Well, GANs were first introduced in the 2014 paper, Generative Adversarial Networks. And GANs use a concept of utilizing the game theory to generate basically new images from an already existing data set. It isn't or based on optimization, which other approaches before GANs were using, but instead it's using a discriminator and a generator neural networks, to basically generate and improve its own results. So a generator results a new image, and a discriminator looks at if the image is fake or if it's real based on a test set. And if it's determines it's fake and it is fake, then the generator will have to improve to get better pictures, and the discriminator at the same time will improve as well. Eventually, this leads to a score as good as possible, and in the end, then we will get realistic newly generated data, which is almost identical to the original data sets, almost as identical even that like we as humans can't really see a difference. Yeah, GANs are used in multi-domains. Like I said, we can use it to generate new pictures, but we can also, for example, use it to create photo filters, like for example in Snapchat, when you can do a filter on your face, and data augmentation to create extra data if you don't have enough data in your data set. But we also can use it for anomaly detection, say for example, to detect cancer in pictures more easily. We also use it for text to image. It's the back algorithm for text to image. So if you type something and an image gets generated, like for example in the newly neural network Midjourney, and also image to image, which for example translates satellite images to maps images. And that's what we're going to talk about more today. Image to image GANs are a translator basically for pictures. So you have one picture, you want to translate it to a different type of picture. And there are 2 or 4 types of eye-to-eye GANs. First of all, there's supervised, where we have a data set that is paired up. So we have one data set that contains, for example, on the left satellite images, and we have one data set that's on the right contains all map images of the same picture, and they are paired up, so the model perfectly knows how to basically translate the satellite image to map image. We also have unsupervised GANs, in which no pictures are connected to each other. That normally happens because there are a lot of exactly the same pictures available, but you still want to transform pictures from one domain to the other. You'll need a lot more data for this type of GAN. Then we have semi-supervised, in which there are a couple of paired up data, but there's mostly still unsupervised data, but there's just enough for the GAN to learn what it needs to do. And then there's few shot data, which uses metadata in combination with a small data set of images. And well, this is all used for two goals. Domain adaptation, which basically transforms the style of an image to a different domain style. You can see that here in the map data set, in which the style of the greenery in the houses is transformed to a new domain, which is the map. Or we can use GANs for style transfer, which changes the complete style. For example, you want to have a person, but the whole person identification or like eyes or like even the whole structure can change. All right, but there are a couple of downsides to eye-to-eye GANs. They're bound to be unstable, and they mostly also lack diversity. But since a couple of years, there are some metrics that can provide good insights into these unstable and lack of diversity metrics. These are the Frechet Inception Distance, which is a quite popular one, and the signed Inception Distance, which has been announced last year. And they both use the inception distance between image data sets to feature to see what the distribution is between those sets. And two data sets would be the generated data sets and the test data sets. So yeah, what's the inception distance? Well, to measure the inception distance, the FID and SID metric use the Inception V3 algorithm from Google. And this basically creates feature maps from all the images in the data sets. And eventually, after creating feature maps for all images, they get put together into a feature vector. And this gets done for both image data sets, the generated data and the original data, and then the distance between those two vectors the distance between the two feature distributions vectors are measured, and then the distance between the two is the inception distance. And that gets calculated through two separate ways, the FID and SID. So we have FID that uses this formula to calculate the distance between the two distributions. And it shows us the closer to 0 means that the distribution of the generated image is closer to the distribution of the ground truth. And so because of that, we want to have it as low as 0. And the range of the FID is 0 to infinity. So the FID can become as high as possible, but you want to have it as low as possible, just so the pictures get better, basically. Then we have SID. This is similar to FID. It measures high correlation to our own vision interpretation, just like FID, and also it uses the inception distance. But it also has the ability, instead of going from a range to 0 to infinity, it has a range of -infinity to infinity. So this metric also has the ability to question the ground truth images compared to generated images. At some point, generated images can become so good that they might be even more diverse or have a higher variation than the ground truth. In that case, you want to lower the diversity. So you need a minus. You need to go minus just so to say that it's getting worse again. SID is part of the CycleGAN algorithm, and we used also their code on the GitHub repository to measure our results. This is the formula, and also again, when the score is close to 0, the Gaussian distribution of the two image feature data sets lay closer to each other. So if it's negative, you want to go up again. All right, then we're going to talk about the data that we used. First of all, we used the facades dataset. This is a data set that's created by the Center for Machine Perception. And this is a paired data set that includes images of different facades, or also known as fronts of buildings around the world, paired to a segmentation of their unique characteristics. And some of the unique characteristics also include, for example, doors, windows, and pillars, like you can see on the left. And also each building has different backgrounds, and well, some might even include balconies or molding. So these are also included in how far as possible. Then we also have the maps data set, and this is created with the Pix2Pix GAN while it was proposed. It's also a paired data set, and like I said earlier, it includes satellite images and map images of that exact same location. But compared to, for example, the facades, it might be a way bigger domain difference, even though, segmentation is still kind of close. It still uses a lot of colors, but maps might be a little bit more different. Then we have Cityscape, and this is available on the Berkeley AI Research Group website, and it's also a paired data set. And it includes images of frontal views of city, and this was from our perspective taken from a car. And it also has a semantic view of the same view to which it needs to transform to. Then we have our GANs, Pix2Pix. We use the PyTorch implementation. And this is the first pioneering high-quality GAN, one of its kind, and also inspired a lot of GANs that followed. It's very good at generating on small paired data sets, image data sets, but as soon as the image data sets gets bigger, you can see that the results are actually quite decreasing. It uses skip connections in the generator, which avoids to overtrain on specific image details. You want to have the image to be as general, or you want to have the GAN as general as possible, so the image gets more general without unnecessary details. It also lacks cycle consistency and style translation, which does mean that it does do domain adaptation, but yeah, it can transfer over or change styles. It also doesn't do consistency verification, so it doesn't check if it's consistent, and Then we also used CycleGAN. This does, compared to Pix2Pix, address the consistency verification, and it was inspired by Pix2Pix. It's the next more known GAN after Pix2Pix. No paired data is required for this one, actually, but it also does work with paired data, so that's why we used it for our paired data objective. It does introduce new loss functions, adversarial, and also includes 2 cycle consistency losses. What it basically does is it can both generate images from the test or from the goal back to the input value, and it can also generate, of course, from the input to the goal, to the target. It can generate both ways, and so for that's why we need 2 cycle consistency losses. Like I said, it has 2 mapping functions, and we used the cycle consistency code from GitHub. All right, so then we get 2 results. On the left, we have the results generated images from Pix2Pix, and on the right, we have the images generated on CycleGAN for facades after 1 epoch, and for CycleGAN after 8 epochs, and for Pix2Pix after 100 epochs. Unfortunately, due to time constraints, we didn't have enough time to train 100 epochs on CycleGAN, and 8 was the max we could go for. But for our objective to measure FID and SID, it's less irrelevant, because you just want to see, okay, how well does it do between the metrics. So after 8 epochs, FID and SID on CycleGAN, for example, both have a pretty high score, but they're better, or at least for FID is better after 1 epoch, but SID is a little worse after 1 epoch, which could mean that SID has or is more sensitive to bad diversity and also variability. It measures both diversity and variability, and FID only measures diversity. So it could mean that in the 8th epoch there was less variability, and that's why the score is higher compared to the 1st epoch. And also for Pix2Pix, you can see that Pix2Pix is starting to generate better and better and better images, and you can see that in both metrics. And also the same for CycleGAN, Pix2Pix and cityscapes. After 100 epochs, Pix2Pix is able to make a pretty good image, while at the same time CycleGAN is still kind of struggling after 8 epochs, which is expected. And these are the results for FID and SID on the cityscape dataset. And yeah, you can see again that for the CycleGAN, SID is performing worse again after 8 epochs. And also you see it this time in the Pix2Pix model that after 8 epochs, SID is slightly higher than after 1 epoch, which would probably mean that, again, the variability is a little worse after 8 epochs, but the probability is that SID and variability gets a lot higher after 100 epochs. Then we have the last data sets, just to verify results, the MAPS data sets. And you can see again that Pix2Pix is performing well because it has 100 epochs. But if we are looking here, then you'll see, yeah, again, SID is a little lower this time, probably because it's easier, because the domain is more different this time, so it's more easier to pick up the variability and diversity, so the results can generate better results. All right, so these are all our results over the 3 data sets and over all epochs. And from this, we can conclude that the FID and SID are closely related to each other. If one goes down, the other normally goes down as well, and if one goes up, the other, we could say, goes up too, except for the few cases that I pointed out earlier. And yeah, we can also say, since SID is proposed last year, that is a feasible alternative to the well-known FID metric. However, SID is a better representation, we would say, on the distance between the ground truth and distribution, as it measures both diversity and variability. And yeah, that's also because it can go to a negative score. So because of that, it's also can weigh higher. That's also why their scores are a lot higher in the first epoch, especially. All right, and then I have some recommendations. We used relatively small data sets. For example, facades is only 606 images big, but maybe results will be different, probably will be different when you use bigger sizes data sets. I would also recommend some more research on the SID implementation. We saw that it had some great benefits to use as a loss function, but maybe we could even use it implemented in the discriminator, just so it could also train on this metric. And I would also recommend just looking at different GANs or data sets, bigger data sets, different GANs, later developed GANs, like for example, Munit, to see what it does on those GANs. And also, I would recommend looking if, for example, data sets with mixed domains. For example, if the facades and cityscapes data set would be mixed together, if that would be of any influence to the FID and SID. If it's mixed domains for only the train set, then the FID and SID should be high because of the high diversity in the distribution. But if it's also high in the train set, then it should be better. All right, and thank you for your attention.